And it is recording, and I do have audio. Excellent. Yeah, we're going to look at this today it's if you don't get anything else out of that last chapter, which you really need to get a lot more than this out of that last chapter, but one of the most important things you can learn is that law of large numbers. What does it actually mean? It does not mean that the results have to even out. And that's what leads to the gambler's fallacy. We'll look at this in more detail as we cover some of this material in the chapter today. Let's start with. We already looked at 4:1 last time. That's where we ended on that law of large numbers. So, in 4:2, we're going to start looking at addition rules for probability. How do you add them? And what this involves is basically whether or not two or more outcomes are mutually exclusive or not. Okay. The example they use here is go to a political gathering. Some of the people at the political gathering are going to be Republican, some of them are going to be independent, some of them are going to be Democrat. Some of them are going to be male, and some of them are going to be female. So, what is the probability that the person is, let's see, how does this phrase it? And a large pool of person might wish to know, if for a person selected at random, what is the probability that that the person is a female or is a Republican? Okay, well, there are three distinct possible outcomes. You can choose a person at random. It is possible that they are a Republican, but not a female. It's possible that they are not a Republican, but are a female. And it is possible that they are both a Republican and a female. The fact is that being Republican and being female are not mutually exclusive outcomes. So, out of you have to consider this when you're calculating probabilities. What if the question was, you choose a person at random, what is the probability that they are either a Democrat or an independent? Well, they can be a Democrat. There's two possible outcomes now. That would be a positive view. That would be a positive outcome. Either a person is a Democrat or the person is an independent. But there is no third possible outcome because they cannot be both a Democrat and an independent. They've got to be one or the other. These are mutually exclusive outcomes. Another phrase that they use to describe this is called a disjointed event. Okay, it's a mutually exclusive event or a disjointed event. Yeah. When two events, A and B, are mutually exclusive, then the probability that A or B will occur is the sum of the probability A plus the probability of B. What are the probability, how many people are total in this case? We're looking at probability of independent or Democrat. Well, what's the probability of independent plus the probability of being a Democrat? How many people at the party are independent? At this gathering, if there are, say there are 200 people at the gathering, 50 of them are independents, then the probability of independent is 50 out of 200. Of the 200 people, say 75 are Republican and 75 are Democrat. Is it? Yeah, it's 75, 150 plus 50. Yep, that's right. The probability of being a Democrat is 75 out of 200. So, if you choose a single person at random, the probability that they will be either independent or Democrat is 50 out of 200 plus 75 out of 200, which is 125 out of 200. That's your probability of choosing either an independent or a Democrat. What if of the 200 people, 190 were female and not 190. 90 are female and 110 are male. Okay? Now, what's the probability of selecting a person at random who is both a Republican and a female? Oh, in this case, wait, what did we say? Republican or female, right? Well, what's the probability that they're Republican? Oh. Plus probability that they're female. $90 out of 200. But how many of those 90 are also Republican? There are 90 women at that group. But how many of them are also Republican? You see, we don't know that. So let's say of the 90 females, 20 are Republican and 70 are Democrat, and none are independent. Okay, well now, what's the probability that that one of those females is both a Republican and a female? It's 20 out of 90. So, of these 90, 20 of them were already counted right here. 20 of these 90 females were part of these 75 Republicans. So they were already counted here. You can't count them twice. So you subtract I'm running out of room. You subtract that 20 out of, I'm not 200, 20 out of 90. And that gives you the probability of selecting one person at random of that person being both, or not being both, but being either a Republican or a female. Now, they give you some more examples here in the book that are actually pretty easy to understand once you've wrapped your mind around what's going on there. The whole point of addition, when you see, and this is something you will learn if you ever study Boolean algebra, when you see a plus sign adding things, that is a logical OR condition. Okay? What you're dealing with here, the only rub you have to take into account is whether or not the two events are mutually exclusive or if they're not. And if they're not mutually exclusive, you have to correct for any that would be double counted. You see what I'm saying? You just have to subtract out any of the ones that would be counted twice or that were counted twice in these initial probabilities. Now, that's the addition rules. It's about logical OR conditions, and it's about, and you need to worry about mutual exclusivity. Now let's talk about multiplication rules. We were talking in this case about A or B, and that gave us cause to add probabilities together. Now let's talk about logical AND conditions. So we're going to say, now we're going to talk about the probability of A and B. When the events are independent, okay? Over here, we had to make sure that they were mutually exclusive. And if not, that had to be corrected. Now, what we have to do is make sure that they are independent. That the probability of the second event occurring is unrelated to the probability. If the first event does not affect the second. If they are independent, then the probability of A and B is equal to the probability of A times the probability of B. It's a product, not a sum. Okay. Again, you studied Boolean algebra. Logical AND is multiplication. Logical OR is addition. Now, here's a good example. And you remember the whole thing about outcomes and sample spaces? Okay. Let's say we're going to flip a coin and roll a single die. What are the probability that we will get a heads and roll a 6? Well, the first thing we have to ask ourselves is, do we roll heads or tails? Okay. Then we have 6 possible outcomes. 1, 2, 3, 4, 5, and 6. Here we also have 6 possible outcomes. So, how many total possible outcomes are there? 2 times 6. 12 possible outcomes. Right? What's the possibility that we roll, that we get both a head and a 6? 1 out of 12. There's only one combination that'll get us both. Now, how does this apply here? What's the probability of getting a head? What's the probability of rolling a 6? How many possible outcomes when you roll a single die? So there's 1 in 6 chances that you'll roll a 6. How do you multiply fractions? Multiply the numerators, multiply the denominators. 1 times 1 is 1, 2 times 6 is 12. That's how you get 1 in 12 chances of rolling a head, of throwing a head and rolling a 6. Now, this was based on the idea that the flipping the coin is not going to influence the probability of any outcome of rolling the dice. They were independent events. What if they were not independent events? When the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are said to be dependent events. They list some examples here. Drawing a card from a deck and not replacing it. Selecting a ball from an urn and not replacing it. Being a lifeguard and getting a suntan. Okay. If you're a lifeguard, that will drastically influence the probability that you might get a suntan. Having high grades and getting a scholarship. Those are not independent. Parking in a no parking zone and getting a parking ticket. Okay, we're going to stick with the first couple of examples. The cards and you draw a card and you don't replace it, that affects the probability of the next draw. Now, I'm going to introduce some notation here. Probability of A and B. This is independent events. If they are dependent events, then the probability of A and B is the probability of A times the probability of B if A has already happened. Okay? That's the probability of both occurring. Okay? Here's the example. What is the probability that if you draw a card from a deck of cards, hey, good morning. You draw a single card from a deck of cards, and then you draw what's the chances of if you draw a single card, that it will be a jack? 4 in 52. Which is what, 1 in 13? Yeah. Okay. What then is the probability that your next card will be a queen? Now you're asking, what's the probability of drawing a jack and then drawing a queen? No. You're on the right track. There's 4 queens left in the deck. But there are only 51 cards left in the deck. And that's not a nice even fraction anymore. But you see how this event, because the card was not replaced, changed the probability of the second event happening. That makes this a conditional probability. So, let's look at here's a good example. They ask, what are the probabilities that if you draw 3 cards from a deck, what are the probability that you will draw 3 jacks? Probability of jack and jack and jack. What's the probability of drawing the jack the first time? 4 chances in 52. What then is the probability of drawing the second jack? No. Now, if you've drawn the first one, there are only 3 jacks left. So now it's 3 jacks left out of 51 cards left in the deck. And then the probability of drawing the third jack, there are only 2 jacks left in the deck, and only 50 cards left in the deck. So your probability becomes 4 times 3 times 2 divided by 52 times 51 times 50. And they did the math in the book for you. And it works out to be 24 over 132,600, or 1 chance in 5,525. Which is like 0.0002 probability. In other words, not very likely. It's a highly improbable event. It happens. You play, well, in 2 times in 10,000 is about how many times it'll happen. So, conditional probability, what I've been telling you, that it's defined as the probability that something will happen if the condition has already happened. Now, they work you through some more examples here with, selecting colored chips and selecting colored balls from an urn and that sort of thing. But you get the idea here, right? And there's something here that's happening that I want to bring your attention to, because this should be the very next thing we get to. No, it's not. Yeah, we're going to ease into it. Is this what's happening right here? Or more particularly, see how it's written there? Where you have these sequence multiplications. Okay, this is we're gonna get to that in just a minute. It's called factorial notation. Do either of you know what factorial notation means? What it is? No? Okay, we'll hit it here just directly. First, let's nail down this fundamental counting rule. We kind of hinted at it last time when we looked at how remember how we looked at how the events counted, how you could count those events. It was just a binary progression. Okay, well, in general, if there is a sequence of n events, in which case the first event has k1 possibilities, the second event has k2 possibilities, the third event has k sub 3 possibilities, etc., then the total number of possibilities of the sequence will be k sub 1 k sub 2 times k sub 3 times k sub n. Okay? Now we looked at this just a moment ago. We said, what are the chances, how many possible outcomes will there be if we flip a coin and roll a single die? Okay? There are two possible outcomes to the coin flip. Heads or tails. And then there are 6 possible outcomes for the coin toss. You can flip the tail, you can flip heads, and then you can roll a 1, a 2, a 3, a 4, a 5, or a 6, and then you could flip a tail and then roll a 1, a 2, a 3, a 4, a 5, or a 6. So K2 is 6. 6 possible outcomes of the die. The total possible number of outcomes, 2 times 6 is 12. This is the fundamental counting rule for possible outcomes. Okay? And again, in Boolean algebra, a logical AND means an arithmetic multiplication. When you see OR, it means add. When you see AND, it means multiply. Now, what if we were going to do 3 events? Where we were going to flip a coin and toss a die, and roll a die, and draw a card. Well, in the case of flipping the coin, there are two possible outcomes. Then we roll the dice, and that leaves 6 possible outcomes. And then we draw a card, and that gives us 52 possible outcomes. So I'm not going to try to draw the tree because I don't have enough room. But in this case, you've got 12 times 52 is 10 times 52 is 104 plus another 10 times 52 is 520 plus another 100, what's it, 624? Excellent. Look at me doing math in my head, huh? Go ahead, trust me to do arithmetic in my head. See how much it costs you. Okay, the point is, you see we've got 624 outcomes. What, and this was where I pointed out yesterday about the binary nature of how the tossing coins became binary, or whatever. If there are two possibilities, there are 2 possible outcomes. You flip the coin twice, now there's 4 possible outcomes. Heads, 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 tails, tails, heads, tails, tails. Flip it a 3rd time, and there's 2 more possible outcomes. Flip it a 4th time, and you've gone from 2 to 4 to 8 to 16 to 32 to 64 to 128 to 256 to 512 to 1024. Power of 1, 2 squared, 2 cubed, 2 to the power of 4, 2 to the power of 5, all the way out to 2 to the power of 10. Okay. So what are the chances of flipping 10 heads in a row? One chance in 1,024. 2 to the power of 10. I did count that right. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. That's correct. Now, I told you we were going to come back to this. So I'm going to ask you, what if you have flipped the coin 9 times and you've gotten those first 9 heads? What are the odds now that you're going to get that 10th head? Say again? Yeah, you're exactly thinking correctly. You're thinking exactly correctly. It would be pretty likely because the chances of flipping that 10th head is still 1 in 2. And it doesn't matter what happened before. That's no longer a question of probability. That's a certainty. That's already happened. And that's the whole point of independent probabilities. You came in a little late. We talked about that earlier, that when you're dealing with or events, the probability of this or that, then you add the probabilities and you have to make certain that they are mutually exclusive. Okay, and if they're not mutually exclusive, then you have to correct for that. In the case of multiplication rules, you're dealing with logical and conditions, where you're saying of this and that happened. and then you have to make sure that the probabilities are independent, that the first event in no way affects the probability of the second event. That makes them independent. This is classically independent. And it's a perfect example of the kind of wrong thinking that people make when they speculate on statistics. It leads to a fundamental misunderstanding of the law of large numbers. Okay? Doesn't mean that they're going to average out. It doesn't mean that they're going to even out. If it did, then that would make that 10th flip of that coin extremely unlikely. Okay? But that's not what the law of large numbers doesn't mean that. The law of large numbers means that right now you flip 9 heads in a row, then you've got 1 chance in 2 of flipping the 10th head in a row. And 1 chance in 4 of hitting 11 in a row. And 1 chance in 8 of hitting 12 in a row. It does not mean that tails is becoming more likely. Okay? What the law of large numbers means is that you keep flipping coins, and the more times you flip, the closer you're going to get to an equal number of heads and tails. Okay? That's what the law of large numbers, it means as you get to larger and larger numbers, the empirical probability is going to asymptotically approach the classical probability. That's all it means. And believing it means more than that is what leads people to making mistakes like the gambler's fallacy. Oh, well, if I've lost 3 times in a row, then I need to bet more because I'm due for a win. No, you're not. You're not due for a win. That's not how this works. It means, if that's the way you gamble, it means if you're really lucky, eventually you'll break even. You could have gotten there if you'd have just stayed home. You were already there. Okay. We looked at, that's the fundamental counting rule. That the product of potential outcomes is the total number of possible outcomes for a sequence of n events. And that brings us to what I was telling you about a minute ago, factorial notation. And yeah, we're definitely, that holiday has definitely blown my schedule. So I am not going to, I don't know. Factorial notation. You need to know this. N factorial is written as n with an exclamation point. You probably got a key on your calculator that has n with an exclamation point next to it. Do you see it? Maybe it's a second function. Doesn't matter. Here's what this means. It is defined as n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1. That is n factorial. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Obviously, 1 factorial equals 1. Here's the only definition you're going to have to remember, because otherwise some of the arithmetic that they're about to introduce will blow up in their faces. 0 factorial is defined as 1. Okay? So they didn't ask me for my input when they made this rule. They just decided all on their own, just like they decided that Pluto's not a planet because they're stupid and they didn't come and ask me for my opinion. Okay, so if it comes up on a test, Pluto is a planet and a cartoon dog. 0 factorial is defined as 1 because 0 times 0 obviously equals 1. Actually, 0 factorial does not mean 0 times anything. Okay? Because by the definition of n factorial, if you wrote 0 factorial, it would be 0 times -1, which it would still be 0. Anyway, this is factorial notation. 0 factorial equals 1 by definition. And now we're going to talk about permutations. If you have 5 objects, how many possible permutations can you make? By permutation, I mean arranging objects in a specific order. Okay? Let's say our 5 objects are the letters A and B and C and D. And boy, this isn't going to work because I'm going to run out of room fast. Let's go A, B, and C. We'll just do 3 of them. Okay, how many possible sequences can we create with those 3 letters? Well, if we start with A, then our next choice will either be B or C. If we start with B, our next choice will have to be either A or C. And if we start with C, our next choice will have to be either A or B. Okay, well, if we've already chosen A and B, then our next choice has to be C. If we've already chosen C, then our next choice has to be B. If we've chosen B and A, our next choice has to be C. If we've chosen B and C, our next choice has to be A. If we've chosen C and A, then we have to choose B, and if we've chosen C and B, then we have to choose A. So, how many complete, total different sequences can we create with those 3 letters? 1, 2, 3, 4, 5, and 6. We have 3 choices and 1, 2, 3, 4, 5, 6 choices. 2 choices for A, 2 choices for B, and 2 choices for C. Once you've made, if you start with 3, you choose 1, you have 2 remaining to choose from. And once you've chosen those 2, you have 1 left to choose from at that point. So the total number of choices for 3 possible objects is 3 factorial permutations. Now, notice, and here's the difference. Here's something that you need to make sure you understand. There's a difference between a permutation and, on the next page, a combination. What combination do we have here? We have A, B, and C. What combination do we have here? A, B, and C. What combination do we have here? A, B, and C. Here we have A, B, and C. Here we have A, B, and C, and here we have A, B, and C. In every case, we have the same combination of A and B and C, kind of like I and am and Groot. He can say anything he wants as long as he can say it in the three words I and am and Groot in that particular order. He has one permutation of one combination of words in his entire spoken language. Here we have 6 permutations of one combination. Now, what if we were going to make how many permutations could we have if we were only going to make 2? If we were only going to use 2 of the 3 objects, how many permutations could we then make? We're still going to have 6 because we're dealing with very small numbers here. But basically what we do is we have 3 times 2 times 1, but then we factor out, we're only going to use 2 of the 3 objects, so we factor out 3 minus 2 factorial from the bottom. Well, 3 minus 2 is 1. So we have 3 times 2 times 1 divided by 1 factorial, which is just 1. Okay, the 1's cancel, and we have 3 times 2 possible permutations. You see how that worked? And it's not always so trivial when you're dealing with a larger number. As an example, let's say we have 6 objects to choose from. And we want to make a permutation. How many permutations of 3 of those objects can we make if we have 6 total to choose from? Now, if you look on permutation rule 1 on page 238, you'll see this is written as NPR. Boy, they really didn't ask me about that one. And it is written as N factorial, the total number of permutations of N objects, divided by N minus R factorial. Okay, which, if you write it out, looks like this. N times N minus 1 times N minus 2 divided by N minus R would be whatever's left over. We'll call it M, where M is equal to N minus R. M times M minus 1 times M minus 2. Okay? Let's put it into practice. How many permutations of 3 objects can we make if there are 6 total to choose from? We have 6 factorial divided by, what's 6 minus 3? That's 3. So divided by 3 factorial, that's equal to 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. What's 6 times 5 times 4? Say again? 120? I'll take your word for it. That means there are 120 possible permutations of 3 objects if we have 6 objects to choose from. Or 120 possible permutations of outcomes, of 3 outcomes from a possible sample space of 6 possible outcomes. Now, how does this compare to combinations? And we'll come back to permutation rule number 2 in a minute. Right here, how many combinations do we have from our simple example? Here we've got B and C. Here we've got A and C. Here we've got B and C. Here we've got A and B. Here we've got A and C and A and B. Well, there's those 2. There's those 2. There's those 2. So even though we have 6 possible permutations, we only have 3 possible combinations. Okay? The combination rule in objects, in possible objects or outcomes, can be formed into how many combinations of our objects is equal to n factorial divided by n minus r factorial times r factorial. Okay? What is that telling us? Notice that n factorial over n minus r factorial, that's just, this part here is just the possible number of permutations divided by r factorial. Okay? What do we have here? We had a total of 6 possible permutations. And but only 1 combination. When we eliminated that 3rd object, and we said how many permutations can we make if we only use 2 of the 3 objects, we ended up with 3 times 2, with this number of permutations, which still worked out to be 6. But but we went from 1 combination to, when we divide that original 6 by, what was our r? We said we were going to use only 2 objects. 2 factorial is 2 times 1. And that brought us down to just 3 combinations. This r factorial is simply dividing out all of the duplicates of those combinations. Does that make sense? Okay. Now let's back up 1 page and talk about permutation rule number 2. The number of permutations of n objects when R1 objects are identical, R2 objects are identical, and RP objects are identical, etc., is, in that case, it's n factorial divided by R1 factorial times R2 factorial times R, whatever the last one is, factorial. They say, oh, R sub P factorial. This is the total number of permutations possible with n objects, or n possible outcomes. This, if 3 of those objects are identical, then this is simply dividing out the duplicates. Again, dividing out the duplicates of the ones that are identical. The example they use in the book is how many permutations can you make with the letters in the word statistics, where they note that there are 3 S's, 3 T's, 2 I's, only 1 A and 1 C. And it turns out that there are still 50,400 possible permutations, even after you take out all of the duplicates. And we're out of time. So how far did we get? We got to 5. We got through 4-4. 4-5 is probability and counting rules. And you know what, I'll cover 4-5 on Monday. If you have trouble with it in the homework, it's really pretty straightforward. You can probably get the homework by reading it yourself. I'll answer questions on Monday. And we'll get through chapter 5 on Monday and Tuesday and be ready for our exam on Friday.